Good morning, I am Devasena. In this lecture we are going to discuss about loop matrix, that is the circuit matrix. This topic is present in the subject circuit analysis under the network topology domain. Loop matrix, capital B suffix A. For a given directed graph, it is always possible to state which branches are involved in the formation of loops or closed circuits or meshes. For a given oriented graph, loops can be identified by marking each loop with orientation of loop current by a curved arrow. This enables to write the nodes in the loop in cyclic order. In complicated networks with many loops, it is available to list the nodes in selected cyclic order to avoid the confusion between oriented loop currents. A loop matrix or circuit matrix is represented by capital B suffix A. For a graph with n nodes and b branches, loop matrix capital B suffix A is a rectangular matrix with b columns that is equal to the number of branches and as many as rows as there are loops. The elements b suffix hk of loop matrix has following values. B suffix hk is equal to +1 if branch k is in loop h and its orientation coincides orientation of loop. B suffix hk is equal to -1 if branch k is in loop h and its orientation does not coincide. B suffix hk is equal to 0 if branch k is not in loop h. Oriented graph with loop orientations is indicated in this diagram. For this oriented graph, various possible loops can be listed as follows. In this graph, we are having 5 circuits. Circuits 1 comprises of 1, 2, 3. Circuit 2 comprises of 3, 4, 5. Circuit 3 comprises of 2 and 6. Circuit 4 comprises of 1, 2, 4 and 5. Circuit 5 comprises of 1, 6 and 3. Above listing can be expressed in the tabular form as here in this oriented graph we have 5 circuits. So these 5 circuits are represented in tabular form as. Now consider circuit 1. This circuit 1 is having branch 1, branch 2, branch 3. These 3 branches are going away from the node, so it is considered as +1. Similarly, the 4, 5, 6 branches are not present in this circuit 1, so its value is 0. Now consider circuit 2. In this circuit 2, we have 0, 0, -1, +1, +1, 0. In this circuit 3, we have 0, -1, 0, 0, 0, +1. For circuit 4, +1, +1, 0, +1, +1, 0. For circuit 5, +1, 0, +1, 0, 0, +1. The tabular form of the circuit matrix B suffix A can be represented in the form of matrix as here. B suffix A is equal to matrix here we have represented the 6 branches and the 5 circuit loops. The branches are represented in the row wise, circuit loops are represented in column wise. The rank of the circuit matrix B suffix A is given by B minus bracket of n minus 1, close the bracket and close the other bracket. Thus, for a network with many loops, the size of the circuit matrix increases. To ease simplification, a smaller subset of the circuit matrix is considered, which is known as fundamental circuit matrix, that is F circuit matrix. Fundamental circuit or F circuit or tie-set matrix capital B. It is a subset of circuit matrix. It is represented by capital B. For a given graph, select any tree and remove its all links. Then replace each link one at a time. It will form a closed path or loop or closed circuit along with some of the tree branches existing. The circuits formed by replacing each link in tree are called fundamental circuits or F circuits or tie sets. It is very important to select the orientation of F circuit to coincide with that of the link completing the F circuit. The number of F circuits equals the number of links. For a graph with B branches and N nodes, the possible F circuits are given by open bracket B minus another open bracket N minus 1, close the bracket, close the bracket. Consider a tree of an oriented graph as shown in figure here. This is the representation of an oriented graph. In this, we are going to consider a tree. Consider figure B as shown below. Twigs are 2, 3, 4 are forming tree, while 1, 5, 6 are the links which are not the part of the tree. This is the representation of the tree. In this, we have considered the twig 2, 3 and 4, while 1, 5, 6 are the links. The links are not the part of this tree. When these links are replaced, we have tree F circuits as shown in figure C, D and E. This is the figure C. This is the figure D. And this is figure E. The F circuits or tie sets are given by writing link entry first and then other branches in sequence as follows. F circuit 1 comprises of 1, 2, 3 branches. This is also called as F tie set 1. This is shown in figure C. F circuit 2 comprises of 5, 3, 4 branches. It is represented in figure D. F circuit 3 comprises of 6 2 branches. It is also called as F tie set 3. This is shown in figure E. We can write this information about F circuits in tabular form, which is known as tie-set schedule. The tie-set schedule for above F circuits is, this is the representation of the tie-set schedule in tabular form. Here we have 3 F circuits. These F circuits are represented, as well as we have 6 branches. Now, for the corresponding F circuits, we have the branches. Hence, F circuit matrix B is given by, this is the F circuit matrix B. This matrix is represented here. The branches are considered in the column wise and F circuits are considered in the row wise. In this oriented graph, columns 1, 5, 6 are links and columns 2, 3, 4 are twigs. The oriented graph is presented here for reference purpose. In this oriented graph, we have considered a tree. In this tree, we have 2, 3, 4 branches. So the branches which are part of the tree are called twigs, and the branches which are not the part of the tree are called links. Now refer figure A. In this figure A, 2, 3 branches are the part of the tree. It is indicated in figure B, and the branches 1, 5, 6 are not the part of the tree. So it is considered to be links. In general, the matrix B is arranged such that the first columns corresponding to the entries of links and then columns corresponding to entries of twigs as given below. This is the matrix representation of the tabular form. In this, we have considered the links first. After that links, we have considered the twigs. It is indicated in this matrix. So B is equal to B suffix L, B suffix T. That is, B is equal to U, B suffix T, where BL is the matrix corresponding to the link entries called link matrix. It is always an identity matrix. B suffix T is called twig entries.